Good day, folks. This is another optimization or linear programming question that I'm going to attempt here and put up a video of. This question for my grade 11s is very, excuse me, similar to one that is in your textbook in the chapter review. It's not the same, but it has the same basic premise. So this is a good practice one to watch the video and then go try the one that's similar. This one says, the stylist at a hair salon cut for both men and women. The salon books 3 appointments for women to every man's appointment, at least. So there's a lot more women going to this than men. And usually there's 120 more appointments in any given week. The salon is trying to reduce or minimize the number of hours that stylists work, and a woman's cut takes 60 minutes and men's cut take 25 minutes. So we're looking for the combination that will optimize the minimum number of stylists working. And how many hours would this be? All right, so there's a lot going on in this question. So where do we start? Well, the first thing I'm going to do is I'm going to let x equal women. So that means the variable for women is going to be x, and y is going to be the variable we use for men. And in my objective function, we're talking about time, so I'm going to put t for time. So where am I going to start? The first thing I'm going to say is x, it must be greater than or equal to 3y. Well, how did I get that? Well, the number of women coming for cuts is at least 3 times greater than the number of men coming for cuts. I also can say that the number of men and women together in total is more than 120 a week. I'm also going to create an objection function. For my objective function, in this case, I'm going to use t for time, and it's going to simply be t, should be x comma y here, is equal to 60 times the number of women, because a woman's cut takes 60 minutes, plus 25 times for the men, because there's 25 minutes for a man's cut. All right. Where do we go from here? Well, what I want to do is I'm going to take these two things and I'm going to graph them, because these are my constraints. So let's go to our graph. I've already set it up a little bit. The first thing I'm going to do in my graph is I'm going to take x and 3y. I'm going to set x equal to 3y. I'll manipulate this into slope-intercept form. Y equals 1/3 x. And from there, I'll plot in some points, basically going up. For every 10 I go up, I go 30 over, and draw on a line. This red line represents this function. For my next thing, what I'm going to do is I'm going to take the second equation, and I'm going to say x plus y is 120. Where did I get that? I got that from my other constraint. Therefore, I'll set y equal to 0, x equal to 0, and I end up with points of up here of 120, 0 and 120, and a point down here at 120 and 0. I connect the two dots, and there's my line. So I've set up 2 constraint lines. I couldn't use this is y and x intercept for my other function up here because they're at the same point. So I had to do it in slope-intercept form. All right, now I have to figure out which one of these is my feasible region. So I have to pick a test point. So I'm picking 150 and 20 because I'm pretty sure it's going to be bigger than both, smaller than this line, but bigger than this line. So I picked 150 and 20. All right, let's go over to my test point. So to test this point out, what I do is I actually put both these values into these functions. So I'm going to use x must be greater than or equal to 3y. So I have 50 and 120. I'll sub that in. So 150 must be bigger than 3 times 20. And yes, it is. 150 is bigger than 3 times 20 is 60. So that one's true. I then put it in for the other one. 150 plus 20 must be also bigger than 120. And it is. So 170 is bigger than 120. So that pans out as well. So that means I can come over here and I can shade in this feasible region. So that means anything in here is feasible to say that that would work within our constraints of our problem. Now we need to find our points of intersection. The points of intersection tells us our optimum values. That doesn't mean there aren't other potential values, but they're not optimum for minimizing wage costs or hours worked. So what points am I talking about? I'm talking about this point right here, which is at 90 and 30, and the point that we already found down here, that's 120 and 0, also is a point. Now, it's true that any point along this line going up, or any point going out here, or any point in my shaded pink area are also part of this function, but they're not the optimum minimum values. The optimum minimum values are found when we have constraints. and that's right here, and it's the intersection points. All right, so what does it mean? That means what I want to do is take this value, 90 and 30, and this value, 120 and 10, and I'm going to take them and I'm going to sub them into my optimization function, or my objective function. So how do I do that? Well, I take t is equal to 60, and I'm going to multiply that by my x value of 90, and then add 25 times 30. That gives me time is 5,400 plus 750, or time of 6,150 minutes. All right, so that's 1. I now do it again for this other point. So t is equal to 60 times 120 plus 225 times 0. Well, that one's pretty simple. That's 7,200. So that means I've got a choice of either 6,150 minutes of wage cost or 7,200 minutes of wage cost. I'm trying to minimize my wage costs, or minimize the hours that I have people working. So this is my min, and I could say that they should staff for 6,150 minutes. And if you're there on a busy week, you'll just have to wait. Thanks, good luck.